Hello, everybody. Let's talk about sampling distributions, a really important idea. So following the example that we did in class, we had this population of a whole bunch of Midwestern college students and their GPAs. That's right, GPA. And we had this process where we would take a random sample. I think the sample size here is 30. So I'd take a random sample of 30 of these students and plot their GPAs. And then you could find the average GPA here. Another name for that is the sample mean. And usually you write the sample mean this way. You write X bar on the top. So I didn't actually calculate this, but let's pretend here that X bar is like 3.3. Oops. And so then you take that average and you could plot it over here as 3.3. How? There it is. Okay, and so then we take another random sample of 30 students and we find the sample mean. And let's say this one turns out to be 3.6. And so then we'd plot that over here. And then we take another random sample of 30 college students and find its sample mean. And let's say this one ends up being 3.1. And so then we'd plot that, here-ish. So if we keep repeatedly sampling, finding the average GPA, also called the sample mean, and then we plot all of those sample means, over time it's going to build a distribution. And that distribution is called the sampling distribution. So what is the sampling distribution? Like, what is it really? You'll notice that every single time we take a random sample and we find the mean of our sample, it's a little bit different. And that's sort of expected because the samples are random. So the fact that they're a little bit different every time is referred to as sampling variability. And the sampling distribution shows you what that sampling variability looks like. So it shows the variability in the things that we're plotting, which are the sample means. So the process that we've done here is actually only an approximation of the sampling distribution. The way sampling distribution is actually formally defined, it would be if we plotted the sample means over all possible samples, I should add here, of size n, and in our example, n equals 30. But without computers, it's pretty difficult to construct all possible samples of size 30. And if the original population is large, then the actual number of samples of size 30 might be too big to plot all of them. So it's pretty normal to approximate the distribution by repeatedly sampling in this way. Okay, so this is sort of the primal process that you want to burn into your mind. There's a lot of different distributions here, and it's going to be important in the future to keep them all separate in your head. So let's take each of these vocab items here and label on the left what each vocab item is describing. So the population distribution. The population is what we're sampling from, and that's shown here on the left. So let's label that. Remember that any distribution can be described by parameters. So the parameters in this case are the mean and the standard deviation. Notice also that our population isn't even approximately normal. It's skew left. Okay, so sample distribution. So I've been talking about a sampling distribution, and that's over here. Let's actually label that one first. So this is the sampling distribution, and we should always say sampling distribution of what? Like, what is it that we are actually plotting from our individual samples? So this is a sampling distribution of means. But how is that different than, I missed it. How is that different than sample distribution? Like a really good quiz question would be, why is the sampling distribution not the distribution of a sample? And hopefully this picture makes it clear. This is a particular sample from the population, and it's got a distribution. But you could have a different sample from the population, and it's got a different distribution. The sampling distribution is the distribution of the means of all of the individual samples. So I just wanted to be clear that if you're referring to a sample distribution, that's the distribution of a particular sample. The sampling distribution is the distribution of all the means of all the samples. So let's go ahead and label this now. So this is a sample distribution. And to round it off, let's look at some similarities and differences between the population and the sampling distribution of means of the population. So clearly they're different shapes. This looks approximately normal, this one does not. However, if you look closely, what would you estimate just visually that the mean of the sampling distribution is? It looks like it's kind of here-ish, which is hard to estimate, but it looks like it's halfway between 3.2 and 3.4. Well, if you were going to actually calculate it, you would find that it's actually the same as the population mean, which is like a cool fact about sampling distributions. So the sampling distribution mean is the same as the population mean. And then the last thing that we did in the activity was we gave an informal statement of the central limit theorem, and I will restate the informal statement of the central limit theorem. The central limit theorem says that the sampling distribution of, well, in this case, this is a more restricted application, but I'm going to say the sampling distribution of means, in our case, is approximately normal as long as the sample size is large enough. And this is a bit of a subjective condition because what counts as large enough depends on how close to normal your original population is and how close you want your approximation to normal be on this other side. But the value that our textbook uses and the value the College Board uses is the sample size has to be at least 30. So as long as each of these samples is 30 or larger, this resulting sampling distribution will be approximately normal. As you saw in class, hopefully, if the sample size is like 3, I'm just sampling 3 students over and over again, and then I make a sampling distribution of the means, it's not guaranteed to be approximately normal. It's going to mirror this population distribution shape more closely. Okay, so what can you do with a sampling distribution? Why do we care about sampling distributions? Eventually, these are going to play the central role in statistical inference, which is the process that you use whenever you conduct any kind of experiment to tell whether or not your experiment had a statistically significant result or not. But there's some nuance there that we'll get to. For now, let's just say that, like we've been doing, if you have a normal model and you have like an outcome inside that model somewhere, the model will tell you how likely or unlikely, how probable or improbable that particular outcome was. So let's take a quick look at an example of that. So let's use the normal model here for our sampling distribution. So the sampling distribution looked like this, but here I've overlaid a normal model on top of it. And I'm going to tell you the parameters for the normal model here. There are ways of calculating these, which we'll get to in a second. So let's say it's got a mean of 3.28, and let's say that it's got a standard deviation of 0.1. So pause the video and go ahead and use your ideas from earlier in the unit to answer this question. What is the probability that we will draw a random sample of 30 students whose mean GPA is 3.6 or higher? You should now be pausing the video and testing yourself. Okay, so I want to find the probability that my sample mean is above 3.6. So I'm going to use normal CDF. So I'll go second distribution, normal CDF. My lower bound, I want to be 3.6, which is kind of here-ish. And I want to find the shaded area that's larger than that. So I'll say 3.6. My upper bound, I'm just going to make a number that's large. As my approximation of infinity. It's a very poor approximation of infinity. And let's see, so the mean is going to be 3.28, and the standard deviation is going to be 0.1. And let's find the probability, and the probability is 6.87 times 10 to the negative fourth. which I've written down here. So that's the same as, so like 6, 8, 7. So let's count 4 places. So 1, 2, 3, 4. Let's see, did we do that right? 1, 2, 3, 4. Yeah. So very, very small chance, like less than 0.06%. And you can look at the original population and see if that fits your intuition. If we just look at the distribution of scores, does it seem likely to you that if we randomly sampled 30 students, it would be that unlikely that their average GPA would be above 3.6? Okay, so let's flip over to the backside. So if you're taking these samples and you want to find the mean of your samples, like a mean is a measure of center for a quantitative variable. But what if we have a categorical variable? So for the example here, the categorical variable is whether or not the student lives on campus. So if you have and this is the, just like before, this is the population. So this is all the students. And this is the proportion of students that live on campus. 77.6% of them live on campus. So if I'm going to randomly sample 30 students, it's like some of them are going to live on campus, some of them aren't. And so this is an example of what a random sample might look like. And what I'm measuring there, since we're looking at the categorical variable of living on campus, is we can look at the proportion of students that have a particular value, like living on campus versus not. So that's my population. Here, individual samples, again, sample size 30, I think. And then here would be the, what's the name of this? Let's label it. Sampling distribution. But remember, I said always write sampling distribution of what? So this is a sampling distribution of proportions. So just a quick sense check here. Why was it exactly that a categorical variable whose only values are yes or no ends up producing a sampling distribution that's quantitative? It's got numerical values there. Because if you hadn't been paying attention this whole time, it might seem like a categorical variable should create a categorical variable like over here. So real quick, see if you can summarize. This is an exercise in concision. See if you can summarize in this amount of space a good answer for why. Okay, here's mine. This distribution is a distribution of proportions. What's a proportion? A proportion is like a percentage, right? It's between 0 and 1. So I would say the answer here is proportions are quantitative. Okay, as before, the central limit theorem applies to this sampling distribution of proportions. I don't know why I made us write this over and over again. So check your idea from the front. What does this mean? I'm not going to show you this. This one we'll debrief in class. So what does it mean to say that the central limit theorem applies to this scenario? Just as a quick alert here, we are hiding some important details. So there's some conditions that need to be met before the central limit theorem applies, and we haven't kind of enumerated what those conditions are, but one of them is that your sample size can't be too large compared to the size of your population, for example. Or if your samples aren't random samples, then it doesn't apply. And we'll look at all that stuff more closely in the future. I just wanted to let you know that they exist, just so that you don't like naively go through your life thinking that the central limit theorem always applies no matter what. Okay, so let's bring it on home. At the bottom of the front page, we'd used the sampling distribution to figure out the probability of getting a particular outcome. But in order to do that, I needed to tell you what the mean and the standard deviation of the normal model that we were using to approximate the sampling distribution actually were. So if you're going to use the normal model, you got to know its mean and standard deviation. So let me now tell you the equations for that, and in a future lesson, we'll kind of learn why these are the way that they are. So hopefully you remember from the front, the sampling distribution of means has a mean that's equal to what? See if you can remember from the front, or flip it back over to the front. Okay, so the mean of this distribution is the same as the population mean. Okay, so what's the standard deviation? It's the same as the population standard deviation divided by the square root of the sample size. So usually the sample size is denoted n, so we'll say sample size. All right, it's a little bit different if you have a sampling distribution of proportions. So in this case, well, the mean isn't different. So if the sampling distribution mean was the same as the population mean, the sampling distribution mean is actually, it's telling you a proportion, right? Because on the x-axis here, we have all the different proportions. So the mean value here is actually the population proportion. So I mean, a different intuitive way of putting this is you would expect that all of our samples should cluster around the true value. And the mean is the true value. And another way of saying what the true value is it's what's actually true about the population. Okay, what about the standard deviation? Okay, for that one I need a little bit more notation. So let's say P is the proportion that's a yes, and let's call N the proportion that's a no. So for example, in the housing situation, we'd said that, yoink, we'd said that 0.776 is the proportion of students who, yes, live on campus. So this would be our P. Our N would be 1 minus P, which is 0.224. And the N is the proportion of students who don't live on campus. So we need the proportion yes and the proportion no. So back down here, the standard deviation is going to be the square root of P times N. Oh. So I should have written this Q. P times Q over N. Let's change this up here also. P and Q are the usual letters that we reserve for proportion yes and proportion no, and then N is the usual letter for sample size. So just to make sure we're clear here, in the scenario we did at the top of the page, the sampling distribution mean should be 0.776. The sampling distribution standard deviation should be 0.776 times 0.224 divided by sample size, which was 30, and then take the square root of the whole thing. Okay, so in our class activities, we'll be working more with these. For now, do a final self-check. So imagine the probability distribution of possible outcomes if I roll a single six-sided die. And we'll call this the population distribution. And so now imagine that I want you to sketch an approximation of the sampling distribution of means if we're going to repeatedly toss 20 dice. In other words, we're going to take 20 dice, roll them all at the same time, and then find the average of all of their values, and then plot that mean. And then we'll do that all again, and we'll plot the next mean of 20 dice. And then we'll do it all again, and we'll plot the next mean of 20 dice. Over time, that's going to build up this sampling distribution. Make an accurate sketch of what the sampling distribution looks like. So not just its shape, but think about its center and its spread. And then go ahead and assume the central limit theorem applies and use a normal model to approximate the sampling distribution and find the probability that we would roll 20 dice and get an average value of 2.5. And then we'll check this one in class.